Hey there, everybody. The purpose of this video is to get you some solutions to this quiz about the Secchi disk and the water clarity in Spirit Lake by Mount St. Helens. So the idea is to check statistically significantly if the clarity has gotten better 5 years after the Mount St. Helens eruption, which makes perfect sense that it should. A quick glance at the data looks like it is. I mean, if your initial reading was 38, and then 5 years later it's 52, 58 to 60, 65 to 72. It looks like most of these are either staying close to the same or being exceeded 5 years later. So the question, of course, is it statistically significant, not just kind of conversationally or approximately significant? So anyway, wanted to get you through the process of that. So I got a template sheet here, and let's fill it out. We are definitely testing an average, since all those things we just talked about were measurements. And that average we're going to be talking about is going to be the difference in clarity over 5 years. Spelled correctly. Thank you. Difference in clarity over 5 years. Now, we have to state them symbolically. State this, the hypothesis symbolically, the mu. So we have to pull mu down to both of these. Okay, copy, paste, mu. Okay, so now we have a decision to make. Let's look back at the original data. Okay, so we got the initial depth and the depth 5 years later. If we think the water is getting clearer, which it looks like it is, I think what we should do is subtract the 5 year later data, subtract the initial data from the 5 years later data. That will give us a positive number if we are correct, and it'll give us a statistically significant number of standard deviations on the positive side if we are statistically significantly correct. So I'm going to go ahead, and I got the TI already set up for us. Oops, that was the wrong one. As far as the, here we go on. I got the L1 and L2 for initial and 5 years later. So in L3, I'm going to put, if it's okay with you guys, L2 minus L1, which should give us predominantly positive numbers, which it does. And we are going to see if those predominantly positive numbers are indeed meaningful. So we are going to try to see if mu is bigger than 0 statistically significantly. Now, your choice as to what to put up here, honestly, it really isn't all that important, because the claim we're testing is down there in H1. You could put a mu equals 0. That's totally fine. Another option would be, I'm going to copy the mu again here. Mu, I'm going to insert a special symbol here. Is what we use in class quite a bit, less than or equal to 0, which is the which is the mathematical opposite of mu greater than 0. Honestly, it really doesn't matter. What matters is that you've expressed your claim properly and you've crunched your data properly. All right, so before we get into the numerical analysis, I'm going to come down here and we're going to make sure we're in red. We are. But two types of error. Okay, so a false positive, a type 1, would be picking this when we shouldn't. So this would be saying that the water is clearer when in fact it isn't. Okay, when in fact it isn't. And then what's cool about typing it is you can express the type 2, saying that the water isn't clearer when in fact it is. Okay. Which type of error would be worse in your opinion and why? Your call. If I had to think about this really quickly, let me think about this real quick. You know, I don't know. Nothing comes to mind immediately as to which I would pick. I'm assuming that the process of clarity is not being determined by anything a human being is doing. So making a decision based on this decision probably wouldn't affect anything because nothing is being done. Yeah, I don't know. Nothing's coming to mind right now, honestly. So I'm curious to see what you guys would put. Which distribution? We are definitely going with a T for this one. Ba-boom, T. As far as the test statistic and the p-value, we're going straight to the machines to get this. We've got the data in L3. I'm going to take one quick aside here, and I'm going to plot a couple things. I am going to plot a histogram of the data to see what the shape is. I'm going to plot L3. And along with that, I am also going to plot a box plot to see if we've got any goofy outliers that might be skewing our average. Ba-boom, take a look at L3. I never check this with proportions because there's no need to, but for averages, you can definitely get, whoa, okay, let's change the window a little bit. Let's scale that back to about maybe 2. See what that looks like instead. Still not 2. Maybe scale it back to 1. Will it let me scale to 1? Let's find out. Okay, it is, but the Y max is terrible. Let's bump the Y max up to 5. All right, so it definitely looks like there's no outliers pulling averages. It's hard to decide whether or not that's bell-shaped or not, bell-shaped enough or not. We can run a normal quantile plot, but now we're going to get lost in the weeds pretty quickly. I was mainly looking for outliers, and I don't see any. So the 14 that popped out at my attention up the top, the 2-digit number difference, isn't extraordinarily large, although it does look positive. It does look positive. 75% of the box plot is to the right of this, so I'm pretty stoked about that. So I can live with this data. So I'm going to run down to a t-test. I'm going to fill in what I need. I have data. I'm testing against average of 0 for sure. My data is in L3, frequency of 1. Yep. I'm trying to see if it exceeds 0. You guys seem to like calculate and draw. I like draw personally just because, whoops. Sorry, let me turn my plots off. I like draw because it shows me the null curve. So I have to run the test again. Hang on. There we go. Calculate, calculate, draw. Boom. And there's our p-value right there. We're about 2.4 standard deviations out. So there's your test statistic. T equals about 2.4 standard deviations out. And of course, if you're that far out and only going further, your p-value, as you saw it on that machine, was about 2%, wasn't it? Yeah, 2.4%. That's pretty small. That's pretty small. That gives you the idea of agreement. How well does your data agree with that null hypothesis that nothing has changed? And this says it doesn't agree very much. It agrees only 2.4% with that null hypothesis. So it sure does appear that the water is clear. I'm going to be lazy. I'm going to copy this right down. It appears that the water is clearer. Now, since we said it appears something changed, we could make a type 1 error. And if up here you said that was your worst case scenario, you might have wanted to adjust your confidence at the outset of the problem. But you know what? Honestly, water looks clearer. It only makes sense that it should be getting clearer as sediments that are floating in the water are settling. So I think the statistics have borne out our logical observations. Anyway, hope that helped, and we'll catch you in class.